Okay, last time when we were talking about the hydrogen energy levels that we can see, one thing I didn't point out was that these get closer and closer and closer and closer and closer together, these energy levels. And if we look right here carefully, it goes between n equals 5 and n equals infinity. N equals infinity is a weird idea, but at that point, that's theoretically called the ionization potential. Ionization potential. That's the energy needed, if you think about it, real careful, potential, to remove an electron from the atom. In other words, if we were to put it to n equals infinity, it would be far enough away and have enough energy to actually escape the atom and go on and be its own little electron, free as a bird in the universe. So the question is, can we use that to our advantage? And the answer is, yeah, we can do experiments that can measure the actual amount of energy needed to ionize any electron in an atom. So amazingly, if we do this experiment, we can make a plot of something like the relative number of electrons and the ionization energy in some weird old units called megajoules per mole. They're that way just so we get nice looking numbers like 5, 10, or here we go, 1.31. Those are all kind of numbers that give us a warm and fuzzy feeling rather than 0.0000000 something. Anyways, according to this, it takes 1.31 megajoules per mole, that much energy, to remove one electron from hydrogen. Well, that should make perfect sense. See how high that is? The height is 1, so that's how many electrons it could pull off. It makes sense that there should only be one electron in hydrogen because that's all we have. So that's pretty simple. If we look at helium, we see something a little bit different. We see there are 2 electrons. This is the height of 2. All that makes good sense, but it takes more energy to remove it. The question is why? Well, right there's the answer. The electron is still being held by the nucleus, but the nucleus has twice the force on it, and this is not quite twice the energy needed to remove it. So there we have it. This larger charge in Coulomb's law, which looks like this, Q1, Q2 over the distance squared, that's Coulomb's law. All it really says is these charges, as they get bigger, the force between the electron and the nucleus gets larger. So if we were to go ahead and look a little bit at, let's say, beryllium, which is right here on the periodic table, has 4 electrons, it would show us, amazingly, that there are 2 peaks, meaning that there must be a second energy level. So what it appears is that we went along here and we went through this, which we're going to call the n equals 1 level, and when we filled it up, we went to the n equals 2 level. There's the n equals 2 level. So there we are. We're at the n equals 2. So we would imagine then if we were to do boron that this peak, by the way, this red guy here, these outer electrons are further away. Notice they're further away, therefore the force is less, and these out here, the lower energy, represents the outermost electrons. So what's important is this boron, we might expect a boron then to have a peak that goes up to 3, and then a carbon to have a peak that goes up to 4. Let's see what we get. Look at this. We get something completely different. Boron, instead of going up to 3, creates a new peak with 1 electron. Carbon has 2. Nitrogen has 3. Oxygen has 4. And if we go here, this one will have a peak for 2, another peak for 2, and then a peak for 5. And then neon has a peak for 2, another peak for 2, and then lo and behold a peak for 6 for neon. 6, 5, 2, 2, 2, and 2. So this is fluorine, this is neon. This is amazing. This tells us that not only are we starting over when we go n equals 1 to n equals 2, but we're also going to take this group right here and separate it from this group as we start doing all this photoelectron spectroscopy. Something about these electrons is different than these. So they gave these names. They called these the p block, the p block electrons, and these are called the s block electrons. More on that will come later, but now we have an interesting thing. The periodic table is starting to take shape, and we can see experiments showing us that this shape is proper.